Talk will be presented by Mandy from Kite, and she will be discussing word embeddings. And also, for the future, anyone is interested to give a talk at one of the next meetups, you can always reach out to me, and then we'll find a slot at one of the next meetings.
So I believe that, just one second. Everybody, first of all, thank you so much for coming and joining us today. It's such a fantastic event, and Mary and folks have done such a good job putting it on. So huge round of applause and thank you. I'm speaking on behalf of Kite. My name is Donna. I'm one of the lucky folks who have been here since the beginning of the founding of Kite. So really excited to be here with our team, seeing the friendly faces and seeing the enthusiasm here. So I just wanted to give a quick thank you and welcome Mandy, our computational linguist here at Kite, because she's now going to blow all of our minds with her intelligence and really, really interesting insights. So thank you again for about word embeddings, and this is also known as feature learning in natural language processing. So I want to start off by talking a little bit about features. Features are numerical representations of raw data that we could use for classification or clustering tasks. We usually pick features based on the relevance of the problem and what we think as experts, as data scientists, will have good predictive abilities to what we want to find. So let's consider a very simple classification problem, a binary classification problem. If we want to classify or want to predict whether or not somebody would survive the sinking of the Titanic, some relevant features that we might choose for this problem would be what passenger class were they in, what was their gender, or where did they embark, are they married or not. So the idea, the concept of selecting features seems very straightforward, especially for numerical classification problems. But what happens when we start working with textual data? How do we do feature learning with text? So textual data, if you ever work with it, it's a very dense, information-rich, very high in dimensions. And it's very hard to do feature learning in a way that will embody the essence of this text. So as you see here, this is a very generic natural language understanding problem, sentiment analysis. We want to classify movie reviews based on how the reviewers felt about the movie. How do we encode this text into numbers in a way that we can start making inference, draw analysis, make predictions? And of course, we want whatever method we use to be automatic and scalable. So the way we do this is called word embeddings. Word embeddings is a very loose umbrella term that is used to describe the collection of methods which we can use to map words to vectors of real numbers. This is really nice because once we map these words to real numbers, we can start using the classification techniques that we're familiar with. We can throw these vectors into a neural network for prediction. We can cluster them to find similarities. We can use the classifiers, the models that we are used to using. Another perk about word embeddings is that it actually creates an algebraic model. It creates this continuous vector space that can be used to represent our text corpus, our understanding of language. So some very interesting features that we can find about this vector space, about this algebraic model, is that we can quantify semantic similarity based on the distance between the words. Since every word is represented by a vector, we could compare similarity, for example, by using the cosine similarity, which finds the angles between the vectors. Or perhaps we can look at Euclidean distance. Another interesting aspect is that in our algebraic model, we can use vector addition to find the relationship between words. So this is an example that you will see quite often for NLP. So the vector to king, the relationship between king to queen is the same as man to women. The only difference here being the gender. We can also infer word tense based on the relations of words, and in this example, country and capital relationships. So word embeddings, as you can probably infer from the name, is on the word level. But this can also be done on other types of granularities. We can embed not only words as vectors, but also phrases or more than one word into a vector. This might become useful if, for example, you wanted to train a classifier to recognize different brands. Some brands like Coca-Cola will be made up of more than one word. You don't want to represent something like Coca-Cola with two different vectors. You want one vector to capture Coca-Cola because it in itself is its own entity. Sometimes, you also want to build character level embeddings. Like for example, you want to build a separate vector for the letter A or for the letter B or for the period. So you might wonder, when does this ever come in practice? Why is it useful? This doesn't give us any information about language. Well, so this is often used in more complicated natural language processing tasks. One of the drawbacks of embeddings is what happens when you encounter a word that is outside of your vocabulary. We're training our embeddings over a fixed size of words. If a new word comes to us, we have no ways of approaching this word. How do we know how to vectorize this word so that it fits within our algebraic model? Sometimes, in some tasks, we'll use character level embeddings to make that inference. It's not a perfect solution, but in some cases it does work very well. In general, there's two main types of word embeddings, and these two groups are divided between frequency-based word embeddings and prediction-based word embeddings. They're used in different purposes, and they both have their unique advantages and disadvantages. So frequency-based embeddings is generally easier to understand, and so this will be the one I'll start off talking about. In frequency-based embeddings, so actually before I start on this, I just want to clarify a few definitions. If you look to the picture, you'll see that the rows are called terms and the columns are called documents. So these are two terms that is commonly used in NLP. A term usually describes a word, but it could also, as we talked about before, describe a different granularity. A term could represent a character as well, or a part of a word. Document is a loose term that we use to refer to as a text entity. For example, a text message could be a document. An email could be a document. A movie review could also be a document. So in frequency-based word embeddings, our goal is to count the number of times a word appears in a document. So see, this matrix shows a relationship between the terms, which is usually the words, and the different documents. We might sometimes, so the elements in this matrix represent the number of times that particular term appeared in that particular document. Sometimes we don't want to just take the straight counts. We want to reweigh these representations. We might do this so that more important terms receive a higher score. So using this representation, we're not only able to vectorize the words, we're also able to vectorize the documents. If you look to any of these columns, this will give you the vector for that particular document. If you look to any of these rows, it'll give you the vector for that particular word. The most simplest form of word embeddings is called the bag of words model, and this is a frequency-based embeddings. This was one of the earliest forms of embeddings, and to be honest, it's not very useful. Usually it's just taught in the classroom setting as a gentle introduction into the world of embeddings. And you can see pretty quickly why that's the case. So if we consider three different documents, and once again, these documents can be anything, any text entities, from text messages to emails to phrases. For the first document, it says, I like math and I hate literature. The second document is, I hate math and I like literature. So the exact same group of words is used between these two documents, but they convey very different meanings. These documents, in the first document, the thing you like and the thing you hate is swapped in the second document. So in a bag of words model, you create the standard matrix between the terms which appear, the words in your vocabulary, and the documents. The bag of words model simply counts the number of times this term appears in that document. So it's very, very straightforward, but doesn't give too much information. All words kind of receive the same weighting of importance. And what's more, as you probably realize, the vector for document 1 and document 2 is exactly the same. This is problematic because they convey very different meanings. So as I said before, this creates an algebraic model, a vector space representation of these documents. If we were to plot these into the vector space, we'd get two vectors, we'd get the exact same vectors. And that might fool us into thinking, oh, these two phrases mean exactly the same thing, when in fact they do not. So this disadvantage of not understanding word relationships or word orders persists with frequency-based embeddings in general. And if you want something that that overcomes this issue, you probably want to look at prediction-based embeddings. So this is a more complicated frequency-based embedding. It's called TF-IDF, and it stands for Term Frequency Inverse Document Frequency. This type of embedding is actually used quite often, especially in the areas of topic modeling or document comparison. So here, you reweigh the counts to create a better representation. You give it a score, and this score is made up of the product between the term frequency and the inverse document frequency. So first we calculate the term frequency. The term frequency is the logarithmic of 1 plus the number of terms found in this particular document. So if this term appears a lot in this document, the term frequency would be very high. If it never appears, then you get 0. For the inverse document frequency, you take the logarithmic of the ratio between the number of documents and the number of documents containing this term. And you multiply these two together to get the TF-IDF score. So what you notice is that a term which appears a lot in one document and not so much in others would receive a very high score. And a high score represents relevance. It means that this term is especially relevant to this particular document. So if we use the previous example with the 3 documents and we vectorize them using TF-IDF, this is what our matrix would look like. If any of you has worked with TF-IDF before, you may have seen a different formula for term frequency and inverse document frequency. Between different textbooks, between different libraries, there's slight changes in this formula. Some of them make the 0 correction. So some of them add a +1 to each of these terms to prevent any of the terms from getting a 0 score within that document. But this is one of the more generally used definitions, and it's the same one that's found in Scikit-Learn, so I just went with it. You might realize that the same issue with bag of words persists with the TF-IDF. You have these 2 documents, which once again embodies the exact same vectorizations, despite conveying 2 very separate meanings. So this raises the question, why would we want to use a frequency-based embedding when there's such a glaring issue? Well, one advantage of frequency-based embeddings is that it's very easy not only to vectorize words, but it's also very easy to vectorize documents. Typically, you would want to use a frequency-based embedding when you come in with the assumption that words found in the same document are contextually similar to each other. When you have a large corpus, you're able to avoid issues like the one we saw before, although many edge cases will certainly escape your model. The applications of frequency-based embeddings is usually found in document classification. So if you want to classify documents, for example, if you want to classify text messages as whether they're spam text messages or not spam text messages, TF-IDF is great for that because it's easy to vectorize the documents and it has a good way of differentiating between the 2 classes. It's also very useful in topic modeling. For example, if you have a bunch of documents and you don't really have class labels for them, you kind of want to cluster them in an algebraic model to find out which documents are similar, what you might want to do is vectorize them all with TF-IDF or another frequency-based embedding, and then plot them in your vector space and either use a k-means clusterer or a different method of clustering to find the similar groups of documents. So I've probably said this many times already, but the advantages of frequency-based embeddings is that it's easy to train on the document level and it's computationally simple. It doesn't take a lot of computational resources to train these embeddings, and for some of them you can even do it by hand. The disadvantages is that there's no real understanding of word relationships. Some people might ask, if I use a frequency-based embeddings, do my embeddings even understand language at all? So these are some of the criticisms geared towards these techniques. And so if you do care about, if you want an embeddings with a stronger grasp of language where word relationships actually come into account, you'd probably look at prediction-based embeddings. So this prediction-based embeddings is also sometimes called neural embeddings. And the reason for that is that they were inspired by neural networks. So neural networks are great classifiers. Well, sometimes they're great classifiers. But at the same time, they're this huge black box solution that the smartest researchers in the world have trouble figuring out. So interpretability with neural networks is a serious issue. And somehow it works, and we just kind of accept the fact that they work. One of the interesting facts about a neural network is that, so we use neural networks to solve a very specific task. I might train a neural network to determine to determine whether or not I survived the sinking of Titanic. I might train a neural network to find out what someone is likely to buy. And this complicated neural network that I'm training solves this one very small specific task. But in order for my network to solve to this task, in order for my network to get to that spot, as a byproduct, it creates a universe, an entire universe that no one can interpret, that no one can, well, very few people can interpret, very few people can understand. So this is this great phenomenon about neural networks. And this kind of raised the question a couple of years back about why are we creating these very complicated networks just to solve this one small problem? Why are we throwing away this entire universe? Why are we disregarding the weights? Why are we only using them for predictive purposes? Why aren't we using them for something else? And then I believe the first researchers to kind of start looking into this and tying it to embeddings were from Google. Somebody thought, what if we train a neural network just for the universe it creates? What if we leverage this universe and use it to strengthen our understanding of language? So before I jump into how prediction-based embeddings are created and their ties with neural networks, I just wanted to give a little bit of background about context. So most embedding techniques are based around this one very important assumption. It's called the distributional hypothesis, and it states that words which occur in the same context share semantic similarity. It's a fair assumption, but it does come with its criticisms. Many people believe that this is an oversimplification of language. That human language is so complicated that a geospatial model like embeddings cannot possibly capture its intricacies. And they're absolutely right. We're left with very rigid, very inflexible methods of quantifying contextual similarity. And even then, it's kind of a leap to say that contextual similarity implies semantic similarity. One of the more popular, so despite this, embeddings work very well, and they are considered the state-of-the-art solutions for interpreting languages, especially for deep learning approaches. One of the definitions that we use to quantify contextual similarity is with a context window. We assume that words which appear together, we assume that words which appear within a predetermined window size are correlated. This window size we can fix, and usually we fix the window size by training a bunch of models and seeing which one works well. So let's use the example of a window size of one word, and let's consider this sentence. The quick brown fox jumped over the lazy dog. If we wanted to find out which words are correlated to the word fox, we'll put it in the middle of our contextual window, and because our window size is one word, we look one to the left of fox and one to the right of fox. This way, from here, we deduce that the words brown and jump are contextually similar to the word fox. Using this definition of contextual similarity, we can start training a neural network. And remember, we're not training this neural network to solve any task. We're training this neural network just for the universe that it creates. So how do we structure our data for this neural network? We have our target word, our class, which is fox. And we have as many classes as there are vocabulary words. We have our predictors, which is the context. And using our previous examples, the context is the words brown and jump. And so this technique is called word-to-vec. And specifically word-to-vec using the skip-gram model. What the skip-gram part means is basically how we determine our target and context. With the skip-gram model, our target is the middle word and our context is the word surrounding it. So once we kind of form our data into this structure with the context words used to predict the target words, we construct a very shallow neural network. This neural network only has one hidden layer and one output layer. The output layer is usually a softmax layer, so it calculates the probability of these context words giving us this particular target word. So this is a sample of what the hidden matrix, the weights of the hidden matrix from the hidden layer might look like. If the first three words of, all of the rows are going to be every single word which appears in our vocabulary. And the columns are going to be the weights of the neurons. So of course, we get to determine how many weights the neurons have. And this is important because this becomes a number of dimensions that is in the vector representation of our words. So here, once we train our neural network, once we get the weights in the hidden matrix, we can vectorize the word quick by taking all of the weights from each of these neurons. So how do you decide how many neurons to put? Because of course, this determines your dimensions. There's rules of thumbs out there with most people saying that between 200 to 300 dimensions is a good call, but it's hard to tell. It's hard to tell without actually doing some training yourself. You know, every data set, every text has its own intricacies, and there's no way of finding that out without doing some testing yourself. So prediction-based embeddings they have a more concrete grasp of language. They still don't understand word order that well, but at least they understand word relationships to a certain extent. As a result, they're usually used in more complicated natural language understanding and natural language processing tasks, such as machine translations. So for example, a translator, and also in question answering systems. So you provide a question, and the network returns an answer. The advantages of prediction-based embeddings is that it has a better understanding of language, especially with word relationships, and the disadvantages is that it's difficult to train, especially on the document level, and it's very computationally intensive. So when Google trained their word-to-vec embeddings, they actually trained it over a web crawl of 100 billion words. So in order to do this on the document level, on the phrase level, imagine how many phrases you would need to make that possible. As a result, it's very hard for most people to train their own prediction-based embeddings. But on the bright side, there's a lot of open source embeddings out there which you can use, but the disadvantage of this being they're not customized to the specific problem that you're trying to solve. So in general, word embeddings they're well regarded. They're considered to be one of the great advancements in machine learning over the past 10, 20 years. They do many things well, and most of their strengths lie in their construction of the algebraic model. This simple model allows us to compute a continuous degree of similarity. For example, if we have two documents and we want to find out how similar they are, all we have to do is vectorize them and compare the similarity of these vectors. We can also compare a query to a document, and this is known as latent semantic indexing. So if you want to find out which document has the answer to your query, you can also find a similarity in your vector space model to determine that. And since word embeddings take textual data and they convert it to numerical data, this allows us to use familiar techniques and algorithms. We can throw our vectors into a logistic regression model, for example, or even into a linear regression model, for example. It allows us to be flexible with our techniques. At the same time, there's a lot of shortcomings to word embeddings. There's a lot of shortcomings to our ability to capture and teach an artificial intelligence the understanding of language. Probably the biggest shortcoming is that term sequence information is lost. As you know, when you say words in different orders, they can purport different semantic meanings. This is not captured at all. Another very big issue is what happens when we encounter a word not found in the training set. So this actually happens a lot in practice because people will misspell words, and they're very creative with their misspellings. You can encounter a misspelling that has never been before encountered in the history of the internet. And there are many ways around this. Most language processing systems, they try to approximate for words that they don't know. Maybe they'll incorporate a spell corrector so that the words can be matched with something in the training set, but there's no perfect solution around. Another issue with word embeddings is issues with data sparsity. So as you see so especially if you're using frequency-based embeddings, as your vocabulary grows very large, you'll notice that in your matrix you'll have a lot of zeros, a lot of spaces of no information. So the issue of data sparsity is a pretty serious issue. And when our textual representations are sparse, this can add noise, which will deter our models, and it means longer computational times. The solution to this is to use dimensionality reduction, otherwise known as figuring out which feature is important and throwing everything else out. So dimensionality reduction techniques are usually rooted in linear algebra. We can use, for example, singular value decomposition to pick out the most important features and throw out the rest. All in all, our understanding of language, what researchers have done with word embeddings, it's great, but there's a lot more room for improvement. And here's a funny comic to conclude my presentation.
Two quick things here. I think you talked about context between words. In simple bag-of-word model, that context does exist. Representation does exist. That's called n-gram representation of words that we can utilize to still get context around words. So trigrams and diagrams are quite common, and they're easy to compute. Nonetheless, they increase the computational complexity, but still they're still easy to compute. Now, word embeddings, even if you could to compute the word embeddings, one of the problems we stated was same representation for two different sentences. That problem hasn't gone away. Even with word embeddings, you're getting the exact same representation. And embedded representation, nonetheless, the same representation for two sentences, right? So how do you take word embeddings and translate them back to your document representation? It's still an active area of research and it's still a problem. So, but they do tend to work. I agree with you there.
Yeah.
Are word embeddings considered like the state of the art of NLP, or is there now like a next layer of something new?
So word embeddings is just a loose term that describes a collection of techniques used to vectorize words. So I guess all the better techniques that you might be thinking about would fall under this umbrella term. So this is just the solution set in general.
Okay.
Yeah.
So you were saying that one thing you could do is take a query and take the cosine similarity of the query to documents to locate the document most likely to answer the query. My question is a technical linear algebra question. Given that the query is so much shorter, wouldn't maximizing the projection of the query onto the document give you better odds?
So we could certainly do that. I believe that most often in the industry, the cosine similarity is taken. But before that, dimensionality reduction techniques are applied to make sure that the vectors are of the same length. But definitely what you're suggesting is very valid. I have never tried that myself, but in theory it could work.
So one of the ideas behind cosine similarity is to address exactly what you're describing, because you're not just measuring angles, you're not measuring the width of the magnitude of the vectors themselves.
Yeah, the first thing you do is divide by the length of both vectors right there in the formula and throw away the magnitude information.
Yes. So it's that angle that you really, and if it doesn't matter if I have a really large vector and a really small vector, the angle between them is still pretty similar, regardless of their magnitude. The angle will still remain similar, right? So that's how we address that. But the magnitude is also useful. I wouldn't say that.
The chance of getting a whole bunch of angles that are very, very similar in value is high.
So you're getting a lot more false positives, right? So if I'm looking for a document and I put the word "the" as a search term, and it picks up every single document because I trigger on the word "the." But if you put on like a longer sentence, now you're increasing the magnitude of your question. Right? So the magnitude does help. However, the cosine similarity, the use of cosine similarity is exactly to not be limited by the magnitude only, to look at the angle itself. Right?
Another point is that these are very high dimensional vectors. So for the likelihood of two vectors to share the same angle is actually not that high.
Oh, no, not the same. Very similar.
Yeah.
If somebody's written 200 documents on a subject, you're going to get 200 angles that are all very similar in value.
Mm-hmm.
I think moving to projection would help you break the tie, but let's talk about that later, maybe.
Okay. So 200 documents is considered very small, with most like.
And then not 200 documents in the corpus, 200 documents written about the topic you're searching on.
Right. Okay.
Within the corpus.
That's certainly, yeah, so the projection is certainly like an interesting suggestion. Possibly it could be worth a try.
So I keep running, the thing you said about people misspelling stuff and the problem with word embeddings is what if the corpus it was trained on did not contain the words that are common in the corpus you want to use it on. And you suggested using spell correctors. But what if my corpus has something like TBT for Throwback Thursday, which the Word2Vec was not trained on? It's not a spelling error. It's something that has meaning. And it occurs a lot.
Mm-hmm.
So in this situation, doesn't it make more sense to use like a frequency-based embedding, where at least it detects that, okay, this is very frequent in the corpus, and maybe if it frequently occurs in two documents, they're similar, and the prediction-based wouldn't be able to tell me that these two documents are similar because to it's just in misspelling.
Mm-hmm. So what you could do is you can incorporate words like TBT, like abbreviations, into the training set for your embeddings. So if, for example, you're using pre-trained word embeddings and you want to, and you have and you know this is a group of words that you will use often to customize your data set, what you could do is train a separate word embeddings over this smaller group, and you can concatenate the two vectors and use that for your inference. But then, of course, you also have the choice of switching to frequency-based embeddings. But if this word doesn't occur very often, it'll still throw off your model.
I think the key message behind embedding, as you mentioned before, is the large corpus to train. Without that large corpus to train on, they're not accurate.
Right. Yeah. Absolutely. Yeah.
I have a question. Are there any attempts to unify the statistical methods with the linguistic ones? I mean, this is a statistical method in NLP, yeah? And the original approach till 2000 or something, 12, was a linguistic one. Yeah? There is this war between linguists and statisticians. Yeah? So if you can assign some semantics besides these word embeddings, so that you have a kind of a structure of the sentence, just throwing an idea there.
That's a great suggestion. Actually, Greg and I, this is something that we're trying to tackle, of combining the more traditional linguistics approaches with some of these approaches using neural networks and seeing if we can combine them to find a better representation. There hasn't been from my understanding, there hasn't been too much research in this area, and it's still a very new and developing area.
So we're looking at taking ontologies from WordNet, for example, and computing similarity low-level similarity distances using embeddings instead of path hopping or frequency numbers coming from corpus, and we're trying to combine it with another.
That sounds very interesting. Another thing that I've seen is that you can train, instead of training it over words, for example, you can train it over parse trees, like the results from a dependency parser, for example.
Yeah. This is a question about the QA question answering. Is there anything in QA that, given a piece of text, the question would be, is the author of the text happy or sad? Or is this text sarcastic? Mm-hmm. Does it have that ability? Does question answering have that ability?
So this isn't really a question answering problem. This is more of a sentiment analysis.
I know, but I'm asking, has anyone used question answering to answer questions of the sentiment analysis type?
You could, yeah. So question answering is still so information. So there are solutions out there to tackle question answering, and in theory, you can ask it any question and it will return the answer. However, Kite, we do a lot of question answering. We have a chatbot, and our clients interact with this chatbot. So from what we've seen so far, question answering systems are not usually as good as we would think they are, especially for quantitative questions like, is this text sarcastic? That would give it a lot of trouble. Yeah.
You mentioned Google Work. Where do they apply it in Google Translate, or what projects they are using? You said that huge amount of corpus they are using.
So that is for the embeddings Word2Vec. So Word2Vec was an embedding method that was originated from Google. So Google at the same time has also released some open source pre-trained Word2Vec embeddings that we could use for our classification tasks. And for this particular set of embeddings that they released, it was trained over a web crawl of 100 million words.
So they don't give any details. For example, what methods Google Translate is using. It's an advanced form of embedding.
I think the latest one is an LSTM.
Oh, okay.
Google Translate. And the LSTM for translation piece is just taken with it.
So on your second or third slide, you had the like king and queen and man and woman, and you were showing how they were similar, or how the difference between the vectors were similar. But in order for that to happen, I'm just making sure that I'm assuming that right. In order for that to happen, the documents in your training data would need to treat the difference between kings and queens similarly to the way that they treat men and women, for example, right? Like nothing magically falls out of the way that the words are, right?
Yep. So
Okay.
this is the benefit of having a large training set. With like a very large training set, you're going to see all of these contextual relationships. And just by inferences of the conditional probability of two words being together, this is created as a byproduct. So what you saw, those two vectors being parallel, is probably not what you would observe with a embedding model, but certainly with the better ones, you would get very close to it.
The
Yeah.
context of king and queen needs to repeat enough times man and woman for embeddings to pick it up in your corpus.
Right, and then it would see, we're talking about kings and queens, we're talking about men and women.
And it'll
I
say
guess
that-
they're related?
Yeah,
Yeah.
exactly.
Right.
If you don't have one occurring in the same frequency, you have a mismatch there.
Right.
Then you may not even detect that.
Right, and if you had a document that was about kings and queens that didn't mention men and women at all, and a document that was about men and women and didn't mention kings and queens at all, it doesn't magically
As long as the
infer that
context
they're
of those two
related.
words are the same, right? So if king said and he did this, and the man said the man did this, or man walked, the king walked, as long as the context of those words are the same, it'll pick it up. However, if you use the word king and queen in a totally different context, and the man in a totally different context, then those vectors will never.
Okay.
Yeah, there's no magic happening here. It's all
There's
it's
no
like
understanding of the words, right?
yeah, it's a
And
mathematical
I suspect
model.
you might get a different result if you fed in a corpus of Harlequin romances as opposed to a corpus of histories of the British monarch.
Probably will.
Absolutely.
Well, you can use King Street and Queen Street.
Yeah, exactly. That's one of the issues, like differentiating between the same words with different semantic similarities. That's always been a challenge. Yes?
So my question is around what objective function are you trying to maximize? Or another way of putting it is, how do you measure that this model is doing something good? Because the language is so flexible that you're trying to compare something quantitative with something qualitative. So do you actually know that you've done something good quantitatively? How do you measure that?
That is a very difficult question. Some of these, like, it's very hard to quantify like how well your embedding methods are. But usually when we create these embeddings, it's to solve a very specific problem. For example, we have like all of these text messages and we want to classify if they're spam or not. We use the vocabulary generated from these text messages and we train embedding models over that. At that point, it's not so much of does my model, like, is language being captured properly, but it's more of let's measure this against our validation, our testing set, and let's see how it performs.
So it struck me that there's a problem with that question, which is that you're not making methods. You're making text embeddings. Then somebody downstream of you has to hit it with a machine learning or classification method. So it's only going to be good or bad in the context of what everything you paired it with to use it as an input?
Right, that's true. Possibly if you were like Google or a large research, possibly if you were like Google or a large research company and you're releasing these open source embeddings, you might be struck with the question of, are these embeddings, these general level embeddings that anyone can use, are they good? Like possibly you might consider that.
For what?
Yes.
Which is what. So you can start from there and train it, right? So there's transfer learning that you can do. You can start with this embedding, and then you can take your own corpus and put it on top of it, learn a more specialized version of that, right? If you're only interested in, let's say, 10, 20 words, you can definitely start from generalized embedding model, and then land up in a place where your master only predicts the 10, 20 words.
Sorry.
Okay, no, sorry, last guy.
Asking for advice. So Word2Vec and Plov, I know them to be pre-trained and used. do you know any pre-trained word embeddings if I really don't want to train it on my own corpus that kind of deals with social media slang and just misspellings? Like, I've heard of tweak to vec, but the paper I saw, because of licensing restrictions, it couldn't release the pre-trained embeddings. It just released its model. Do you know anyone?
So I don't know any prominent word-to-vec or glove embeddings that would deal with the issues of slang. However, there's also a different type of embeddings called fast text. And while fast text doesn't deal with slangs, their advantage lies in their ability to learn words outside of the training set. So, so this would work well with misspellings and uncommon slangs.
Okay. Fast
text.
Fast text.
It's my Facebook.
Okay.
So, thank you very much for your help.